We have previously discussed the ideas of an even function and an odd function, and we want to talk about it a little bit more here and discuss the even and odd identities, or also called the negative angle identities. A function is even if evaluating the function at a negative value and at a positive value gives you exactly the same result. So for example, if we were evaluating cosine of negative pi over 6, if it's an even function, this should be equal to cosine of positive pi over 6. So positive pi over 6, that cosine value would be right here. That would be positive square root of 3 over 2. And negative pi over 6 would actually be coterminal with 11 pi over 6, and that x value is also square root of 3 over 2. So when we talk about our even identities, we're talking about cosine and secant. These are both even functions, and cosine of a negative angle will be equal to cosine of a positive angle. Secant of a negative angle will be equal to secant of the same positive angle. The odd functions would be sine, tangent, cosecant, and cotangent. And when we're talking about an odd function, we mean that if we evaluate the function at a negative angle and at a positive angle, their outputs would have exactly opposite signs. So for example, if we evaluate sine of negative pi over 6, and of course that would be right here, we just talked about that, that would be negative 1/2. This would be equivalent to minus, or the opposite sign there, of sine of positive pi over 6. So when we look up here at positive pi over 6, that's a positive 1/2. So their outputs have opposite signs, and we can make them equivalent by putting a negative in front of that positive angle. So negative 1/2 equals to negative 1/2. So we're talking about odd functions. We're basically saying that the negative on the inside is equivalent to having a negative on the outside. So for example, if we knew that tangent theta was equal to 2.6, and we were asked to find tangent of negative theta, using our definition of an odd function, tangent of negative theta would be equal to minus tangent of positive theta. So the negative on the inside can come to the outside. Well, we already know that negative tangent of theta, well, we already know tangent theta is equal to 2.6. So let's substitute tangent theta with 2.6. So now we would say that tangent of negative theta would be equal to negative 2.6. So the outputs would be the same numbers but opposite signs if the angles on the inside are same values but opposite signs. Cosine is an even function, so cosine of negative 2 pi over 3 would be equal to exactly the same thing as cosine of positive 2.3. So if we know that cosine of positive 2.3 is a negative 1/2, then we know that cosine of negative 2 pi over 3 would also be equal to negative 1/2. Sine of negative 2 pi over 3, since sine is an odd function, this would be equivalent to negative, or the opposite sign of sine of the positive angle. So if I put positive 2 pi over 3 on the inside, sine of 2 pi over 3 would be equal to square root of 3 divided by 2, and we'll bring our negative out. So sine of negative 2 pi over 3 would be equal to negative square root of 3 divided by 2. Now we want to discuss the idea of multiplying trig functions. So here I have cosine theta, and on the inside of the parentheses we have three terms. We have cosine theta, minus sine theta, and plus 2. So we're going to do what we would have done in algebra. We're going to distribute or multiply the cosine theta function times each of the three terms that are on the inside. So we will distribute. When we multiply these functions together, we will write it as cosine theta times cosine theta. It's important to remember here that we are not multiplying the thetas together. And it's also important to remember that a trig function is never separated from its input or its argument. So it's always cosine of an angle. So we have cosine of an angle times cosine of an angle, and that gives us cosine squared of that same angle. And then we're going to distribute minus, so cosine theta times negative sine theta would be minus cosine theta times sine theta. And there's not another way to write that. So we're just going to write it as cosine theta times sine theta. And then cosine theta times a positive 2. That gives us 2 times cosine theta, which we're going to write as plus 2 cosine theta. So it's very much like algebra, except we want to be careful as we pay attention to how we actually treat those trig functions and their inputs. In the next example, we are multiplying two binomials together. In other words, we have, within the first parentheses, we have two terms, and in the second parentheses, we also have two terms. When we multiply two terms times another two terms, we use FOIL. So first times the first will give us 6 sine squared theta. Outer times the outer will give us plus 8 sine theta. Inner times the inner will be minus 3 cosine theta times sine theta. And last times the last, negative times the positive, we get negative 4 times cosine theta. Notice that we don't have any like terms. When we talk about combining like terms, we need everything past the number to be identical, and none of these terms have an identical matching portion following the numbers. So this would be our final answer. Nothing else can be combined once we do the multiplication. If we have 2 sine theta minus 1 squared, so everything here in the parentheses squared, they have two terms inside of the parentheses squared. We will write this out twice. When we square something, that means to multiply it times itself. So we will write this out twice and then FOIL. So first times the first gives 4 sine squared theta. Outer times the outer, we get minus 2 sine theta. Inner times the inner is another minus 2 times sine theta. And then last times last, negative 1 times negative 1 gives a positive 1. Now we want to see if we can combine any like terms. So we look past the numbers for each of our terms, and we want to know if we have any matching portions. Well, the two middle terms have exactly the same matching portions that follow the numbers. So we can actually combine those like terms. So 4 sine squared theta won't combine with anything else, but minus 2 sine theta and minus 2 sine theta, we combine the numbers in front and keep exactly the same matching portion. So minus 4 sine theta, and then we bring down our constant plus 1. So our like terms are combined exactly the same way they are when we are in algebra. If you think back to your algebra days, when we had two binomials multiplied together, so here we have two terms in parentheses times another two terms in a set of parentheses. If you look at these two terms and two terms, you notice they're exactly the same. They look like two binomials that are exactly the same, except they have opposite signs in between. We would call these conjugates. And something special happens when I multiply two terms times two terms when they have that relationship of being conjugates. First times the first, so we're going to FOIL. You get tangent squared theta, outer times the outer, plus tangent theta times secant theta. inner times the inner, we get minus secant theta times tangent theta. And then minus, last times the last, we get minus secant squared theta. Now we want to combine like terms, and we look past the numbers, and of course all of these are implied ones for the numbers out front. When we look past the numbers to see if we can combine any like terms, we see that the middle two terms both have tangent theta times secant theta. And so these are like terms, and we can combine them, and we combine the numbers out front. Well, plus 1 minus 1 gives us 0. So these two middle terms end up canceling each other out. So we end up with tangent squared theta minus secant squared theta. And another word for this, we could call this a difference of two squares. Perfect square minus a perfect square. Now we want to look at doing the opposite of multiplication, and that would be factoring. When we factor, the first thing that we do is we look at all of the terms that we have, and we divide out or we factor out a common factor. So we want to look for what they have in common. And we notice that sine alpha and sine alpha is common to both terms. And it's important that not only the trig function have the same name, but also the input must also be the same. So we must have an alpha and an alpha in order for us to say that we have a common factor of sine alpha. So the input is also important. It must also match. So both of these terms have a common factor of sine alpha. So we'll divide out or factor out to the front that GCF of sine alpha. And on the inside, we would have left cosine alpha minus secant alpha. If we wish to factor sine squared theta minus 1, we have two separate terms, and both of these would be what we call perfect squares. So we're going to think back to algebra when we factor something called a difference of squares. And when we're factoring, let's think about, back to algebra, think about back to this example here, x squared minus 1. When we factor that, we factor that as conjugates. So it's the first term, whatever I'd have to multiply times itself to get x squared, which would be x and x. Basically thinking about the square root of x squared, and the square root of 1 would also be 1, and we put opposite signs in between. So difference of squares always factors as what we would call conjugates. So if I'm factoring sine squared theta minus 1, we will also factor this in a very similar way. But instead of putting x, what we're going to put in the front of both would be sine theta. Sine theta times sine theta gets me back to sine squared theta. We will have opposite signs in between, and then we have that 1 for the last two parts of our parentheses. Now we want to factor 4 times tangent squared beta plus tangent beta minus 3. Once again, I would encourage you to think back to your days of algebra. And every time that you see a trig function, you can start to think about that as being sort of like x in algebra. So we can say that this is similar to the idea of factoring 4, and instead of thinking of it as tangent squared beta, let's think of it as x squared. So that's like x being squared, and plus tangent beta, let's think about that as x minus 3. If you were to factor that in algebra, what would it look like? Well, that would be 4x and x. The signs would have to be opposite, so let's say minus and plus, and then we would have 3 and positive 1. And let's check it to make sure that this gives us back what we want. First times the first gives us 4x squared. Outer times the outer gives us a positive 4x. Inner times the inner a negative 3x, and then last times the last a minus 3. So when we combine the two middle terms, we get positive x. So that's how we would factor that in algebra. Now what does it look like in trigonometry? Very, very similar. We're still setting up our two parentheses for those three terms. And instead of having 4x, we're going to have 4 times tangent of that angle beta times tangent beta. Plus and minus, so we have minus 3, and then we'll have plus 1. So wherever we had x before, now we're just using tangent beta. And of course we can always check that. So let's check. First times the first gives 4 tangent squared beta. Outer times the outer gives positive 4 tangent beta. Inner times the inner is minus 3 tangent beta. Last times the last, negative 3. And we see that the two middle terms would combine to give me positive tangent beta, which is exactly what we started with. If we want to factor cosine to the 4th x plus 2 cosine squared x plus 1, we're going to think back once again to algebra. So we're going to think about what this is similar to. If we were to factor, so we're going to take cosine raised to the 4th power of x, and we're going to represent that as, let's say, like y. So let's say y to the 4th plus 2 times, and this is cosine squared x, so let's think about that as a variable squared, so y squared plus 1. If we were going to factor that, we would use the same process. We would use reverse FOIL. We have y squared and y squared, and both signs are plus, and we would have to put a 1 in the back of both. And of course we can check this to make sure that it really does give us what we want, but this is how we would factor in algebra. Now how are we going to factor in trig? We're still setting up our two parentheses for those three terms, but instead of putting in x, we will now put in cosine squared x, cosine squared x, very similar to how we did y squared and y squared, plus 1 and plus 1. And let's check that on the trig version here to make sure that if I multiply these back together, cosine squared times cosine squared would be cosine to the 4th x. Outer times the outer would be plus cosine squared x. Inner times the inner would be plus cosine squared x. And then last times the last would be plus 1. Our two middle terms would be like terms, so we can combine those to get 2 cosine squared x plus 1. So this checks out. So our final answer here for the factorization of that trinomial would be cosine squared x plus 1 times cosine squared x plus 1. Now we wish to factor sine raised to the 4th power of x minus tangent raised to the 4th power of x. If we think back to algebra, this would be similar to, and we're going to replace, let's think about thinking of sine as a variable like x to the 4th, and tangent as a different variable, let's say y to the 4th. This would be a difference of squares, and we could factor this as conjugates, x squared plus y squared, x squared minus y squared. But the first one would not factor anymore. That would be prime. Sum of squares is prime. And then x squared minus y squared could actually factor down more as x minus y and x plus y. So that would be our complete factorization of that in algebra. But in trig, we're going to do something very similar. So we are going to think about this as a difference of squares, and we will first factor this as sine squared x plus tangent squared x times sine squared x minus tangent squared x. So initially it factors as those conjugates, but then anything that can be factored down more, we would like to factor it more. The first one is like a sum of squares. That will be prime, so we will not factor that anymore, but we still need to bring it down. And then sine x minus tangent x would be the factorization for the difference of squares. And then that would be sine x plus tangent x. So this
Now
would be
we
the
want to look at
complete
the
factorization,
idea of
very
adding
similar
and
to the
subtracting
complete
fractions when
factorization
trig
that we would have
functions
done
are involved.
in algebra.
Anytime that we add or subtract fractions, we have to have a lowest common denominator. So we need these to